So welcome to Light and Sound. We're now on lesson number 7, where we're going to be looking at properties of light. And the 3 properties we're going to be looking at are polarization, dispersion of light, and the electromagnetic spectrum. So in lesson 7, part 1, we're going to start with polarization. So go to your notes on polarization in your book. So let me explain this concept of polarization. It's a little bit tricky to understand the concept. Let's say I've got a rope. The other end of the rope is attached to some fixed base. And I'm going to oscillate the rope. So if you like, this is going to be my oscillator here, which could be your hand shaking the rope up and down. Well, if you hold your hand here and you shake the rope up and down, you're going to send a wave down the rope. You're going to send a wave down the rope like this. So we've already talked about this when we did waves earlier. There's a wave. It's vibrating in just one plane. Actually, along the plane of the board. We would call that a polarized wave. What do I mean by a polarized wave? Well, I say a wave is polarized if it vibrates in just one plane. I could vibrate it in another plane. So, for example, my oscillator in my hand could be vibrating it from side to side. What kind of wave will I get? Well, maybe some wave going out to the side like this, a little bit hard to draw on the board. But this wave is going out perpendicular to the board. That would be a horizontally polarized wave. So depending on which way your hand moves, you will generate a wave along that particular plane, and it's called a polarized wave because it's just vibrating in one plane and one plane only. If we're talking about generating light waves, well, light waves are generated by vibrating charges like an electron. So, for example, if I have an electron there, and that electron vibrates up and down like that, well, it's going to generate a light wave. And the light wave will travel out like this. That there is an electromagnetic wave. It's a little bit more complicated than that. We'll talk more about that detail when I do the third part of this lesson. So it generates vibration charges or electrons, generate light waves. Again, that there will be plane polarized. So the electron is just vibrating in a particular direction and it generates a plane polarized wave. Now, what happens if we're talking about a light source? So a light source will contain electrons vibrating in all kinds of different directions. So any kind of bulb, for example, will have electrons vibrating up and down like that, side to side like that, side to side like that. Every direction possible. So what kind of waves are you going to get coming out from, let's say, a bulb where electrons are vibrating in all possible directions? Well, when it's vibrating up and down, you're going to get that vertically plane polarized. If it vibrates from side to side, you're going to get it going something like this. Pretty hard to draw on the board. Another direction, it'll vibrate something like this. So, what's coming out from a light bulb is waves that are vibrating in every plane possible. So we call that kind of wave unpolarized. Unpolarized waves vibrate in all planes. So you've got that definition in your notes. So in my notes it says, down here, here's your definition at the bottom of the page. A wave is polarized when it vibrates in a single plane. It says after passing through a polarizer. We'll see that in a minute. Unpolarized waves vibrate in all planes. So next I'm going to do a little bit of analysis on my polarized or unpolarized waves. I'm going to pass them through obstacles with little gaps in them, as you can see here and here. Let me have a look at that in detail on the board. So let's say if the electron I've got an electron in a bulb vibrates in all different directions. It goes up and down, it goes side to side, side to side, every direction possible. Then it will generate waves in all possible planes. And when you've got all the different planes, we call that unpolarized. So I have a wave that goes along like this. I have a wave that goes from side to side. It's a bit of a mess, hard to draw on the board. But there is a non-polarized wave that is going towards an obstacle. So here's my obstacle. I'm calling the obstacle a polarizer. Because what the polarizer is going to do, it's going to turn my unpolarized wave, which is vibrating in all planes, into a polarized wave where it just vibrates in a single plane. So I have this gap here. You see that gap AB? It is only the wave in a plane parallel to that gap that will pass through. All the other waves will get blocked. So this vertically polarized wave, that will pass through. So I've turned an unpolarized wave into a plane polarized wave by passing it through a little gap. It's only the wave that's parallel to that gap that passes through. I have a second obstacle here. Now this second obstacle here is going to be called an analyzer. Now you can see that my analyzer also has a gap. This gap is parallel to the polarizer's gap. So, therefore, that wave passed through the first gap. Well, it's also going to pass through the second gap. Let me do the same thing again. So once again, I've got my electron. It vibrates in all different directions because it's the light, say, coming from a bulb. As a result of that, we will generate unpolarized light vibrating in an infinite number of planes. And then I pass it through an obstacle called a polarizer. And it's only the wave that is parallel to that gap that will pass through this vertically polarized wave. Now I come to a second gap. My analyzer. This time I've rotated the analyzer so that the gap is perpendicular to the gap, the direction of the gap in the polarizer. Now that wave that got through, it's going to get blocked because the plane of that wave is perpendicular to that gap, so it can't pass through. So basically, what happens? Well, no light will pass through. It will be darkness on the other side. Now, here's an important point. It's only transverse waves that can be polarized. Longitudinal waves cannot be polarized because they have a kind of a back and forward movement as in a sound wave, so they don't have planes of polarization. So longitudinal waves cannot be polarized, transverse waves can. So it's important to remember that. I have that highlighted very clearly in the notes. It's not really a definition, but it's something, that needs to be highlighted. Only transverse waves can be polarized. Okay, the next thing you need to know in this part of the lesson on polarization, I need to know a demonstration experiment to show that light is a transverse wave. Well, didn't we say this? We said that only transverse waves can be polarized. So if I want to show that light is a transverse wave, I want to show it can be polarized. So the fact that light can be polarized shows it's a transverse wave. We'll keep that in mind. So I'm going to use, in my demo experiment, I'm going to use two Polaroid lenses. Let me explain this in detail. Remember, when you do your demo experiment, you've got your three headings: apparatus, method, and observation. So anytime you do a demonstration experiment, all I want is a nice simple diagram followed by those three headings with just one or two simple sentences to follow. So let's have a look at this demo experiment in detail. So what are Polaroid lenses? Well, they're the sunglasses that you wear. And they have materials made up of crystals that are beautifully set in parallel to each other. So inside your glass, you have these lovely parallel gaps. So that's your polarizer. When the light passes through there, it'll go from being unpolarized light to polarized light. And what does that do? It'll cut down greatly on the glare, so you'll be able to see more clearly in sunlight. Now, my apparatus is two Polaroid lenses. So what I'm going to do is this. I'm going to get two Polaroid lenses, and I'm going to line them up so that the gaps are parallel to each other. So what happens is, the light that passes through one will also pass through the other. That's exactly the same as what we did with the polarizer and the analyzer. This situation here. So in other words, polarizer gap and the analyzer gap, they're parallel to each other. So the unpolarized light turns into polarized light. And because those gaps are parallel, that polarized light will pass through the analyzer. That's the situation. So when the gaps are parallel to each other, what happens is light will pass through here. You'll see light passing through there. Then in the method, you're going to rotate that second lens until eventually the gaps are perpendicular to each other. So what happens? Well, going back to my previous diagram, when the analyzer's gap is perpendicular to the polarizer's gap, well, that polarized light that passed through the polarizer can't pass through the analyzer. So you get no light or darkness. So in this situation over here, you end up getting total darkness in that place where they overlap. So no light whatsoever will pass through there. So you're talking about polarization taking place. You're talking about light must be a transverse wave because it can be polarized. So what does it say in our notes in the method? So the first part is apparatus, and the method is rotate two pieces of Polaroid with respect to each other. And what's your observation? My observation is the light transmitted through the overlapping section goes from maximum brightness, that's here, to darkness, that's when the gaps are perpendicular to each other, that's here. So that's your demo experiment. And also know this in the box very well as well. Only transverse waves can be polarized. The fact that light can be polarized shows it is a transverse wave. Finally, I want you to look at some real-life applications of polarization. This is called STS, Science, Technology, and Society. The first one is polarization by reflection. So when you look at the surface of water, a lake in sunlight, an awful glare can come off the water. Well, wearing Polaroid glasses can reduce that glare or shine. Stress polarization. You can find out if there's a certain weakness in a material. So if you put a material like perspex between two Polaroid materials, which are at right angles to each other, so if you then put the perspex under stress by bending it, you can see certain colors. This thing is called photoelasticity, and it's used by engineers to analyze stresses in components to see if there's any weak spots in the component. So just read through your real-life physics, STS as I call it, and familiarize yourself with it. Right, so that's the end of this particular lesson. There isn't much to know other than knowing the definition of polarized waves, know the demo experiment very well, and know that only transverse waves can be polarized. That's important. So that's the end of the lesson.